Hello everyone, my name is Lamia Albani and I'm going to be discussing today generative design. I have done a research on exploring the multi-objective optimization using specifically Octopus plugin. So what is generative design? Generative design is an iterative process. It explores design outputs using advanced algorithms to quickly perform genetic optimizations of a given model by the designer, the architect. So generative design process evolves each design solution over generations, and it improves the solution over generations. So the model the optimization model has to contain parameters, constraints, and goal values that is fed by the designer. In other words, this process cannot happen with either or. It needs the designer and the computer. So it needs the artificial intelligence and the human creativity to generate permutations of solutions for complex problems. What are the benefits of generative design? Why should we use generative design? Why should we consider it? Why should we even study it? Generative design is a way to be denser, faster, and more efficient. It allows the architect or the designer to start with the goals and the requirements instead of starting with a sketch or a form that has a little bit of a bias from the architect or the designer. It is about reversing the design development way, and instead starting with the actual reality, the actual real life constraints, the actual real life requirements, and the actual project's scope. So starting with this instead of starting with a form or two that do not necessarily address the full scope of the problem. Design problems are usually complex with conflicting requirements that the mankind cannot necessarily understand or is not even formatted to understand the full scope of all of the values and parameters and consider that in preliminary sketch. So evaluating them in traditional ways is almost impossible and would take many practitioners in charge and can be also time consuming. So to sum up, generative design is easy, efficient, cost effective, fast, and reliable. How is generative design used today? These are some really few examples of many other examples out there. I chose these three. I thought they're interesting. I'll start with Zaha Hadid's Architects Haidar Center, and it's located in Azerbaijan. This center has so many sophisticated curves that are not really random, rather studied and computed, and is a generative design outcome based off human creativity and artificial intelligence. The second picture, or the precedent in the middle, is Autodesk's new Mars office in Toronto, and it's also one of the largest scale buildings that were fully designed using generative design. They considered so many new modern techniques to design this space to be very user-friendly and user-oriented. The third image on the left is the acoustical ceiling in Voxman School of Music Concert Hall, and in Iowa, and this acoustical ceiling was also generated using algorithms and parameters and constraints to be able to generate the curve of the ceiling and the penetrations, the shape of the penetrations and the amount of them, also the structure of the ceiling too. So this building is designed by Zaha Hadid's architects. Location is Baku, Azerbaijan, and it was built in 2013. It's an iconic curves generated from parameters and computations using design automations. The building's form and geometry, structure and materiality was a result of co-creative technology. This technology involves the combination of the artificial intelligence and the human creativity. The form is very carefully planned and generated using algorithm that provides a high performance interior space and a responsive building to the surroundings. This Autodesk building is designed by the Living Autodesk, is located in Toronto, Canada, and it was built in 2017. This building is a new 3-floor building, and it's this facility is a hallmark of high-tech office. It's the Living, they use computational workflows and generative learning to optimize the design goals and create a space that takes into consideration the welfare of each of the 250 plus individual employees who work there. So it was very well thought, very customized to the user. So they started with defining the design constraints and objectives. Some variables were fixed and obvious, and for example, the dimension of the floor plates, the number of employees, for example. Others required more planning, such as the number and square footage of conference rooms. All of these were taken into consideration when determining goals for the space, such as access to daylight and views to outside, and various levels of distraction and staff interconnectivity. This is the University of Iowa's Waxman School of Music Concert Hall, and this was designed by Elliman Architects and Newman Monson Architects in Iowa City in the year of 2008. It features custom acoustical systems, and it is a result of an intensive collaboration between architect, acoustician, and machine to design a theatric acoustical ceiling and undulating element of aluminum composite panels. So here is the perforation key on your right, and on the bottom is the acoustic analysis of this Waxman School of Music Hall. The architects used parameters modeling to integrate acoustic reflection, stage and house lighting, fire suppression into a single eye-popping ceiling system. The reflector feature an aesthetic, seemingly random, but highly specific pattern of geometry that aims to blanket the room evenly with sound, while also providing spaces for things like audio speakers, lighting, stage lighting, fire protection. It is very, very intelligent, and it can only be done using these highly specific patterns and studies and computations. So the question is generative design going to replace the creative process of a human being? The goal of this methodology is not to replace, but to co-create and co-design. The human defines the problem and sets up the optimization, so the human really feeds the computer model using parameters and constraints that are usually very complex and often contradicting. The computer then algorithmically generates tens of thousands of solutions that we as humans are not formatted to explore ourselves. These solutions inspire us to think about the problem differently. And the graph on your right shows you what the human does and what the human controls versus what the machine breeds and selects. And the result or the outcome is really a combination of both the visual judgment of the human, the objective function, the problem definition. It is a co-design methodology. So the generative design workflow, the generative design framework can be applied to very diverse set of problems and at many different scales of projects, starting from industrial components, really small industrial elements, to moving to an architectural building, a full-scale building, all the way to an urban design of a city. So generative design can really work with all kinds of different scales. So the workflow, the typical workflow of generative design, it starts pre-generative design. It starts from you, the designer. You input the constraints, the requirements, the goal values. You input all the information. For example, what you want in your Grasshopper canvas. This is what you input, and then the generative design engine generates. So the generation happens using your parametric model. It's recursive, so it is repeating over and over again. It does some evaluation to evaluate these solutions with the goal values and with the constraints and the requirements that you input at the beginning. And then it goes to evolution to optimize the results and start taking away the results that are far away from being close to goals and keeping the solutions that are more accurate towards the end, and keep generating from the most accurate solutions. And then we reach the final post-generative design stage where the human come again to select. So the human component comes in place to custom analysis, identify the trade-off each solution along with the design goals. So it's a process of a manual refinement and doing the takeoffs discussions with the stakeholders or with the clients. And this graph is from a case study that I looked at. It's a sustainable timber high-rise structure done by a collection of students. It's a capstone master's project, and it actually works to generate design using Octopus plugin. So it was very interesting study for me to look at, since it's using the plugin that I'm interested to learn about. So here is the workflow for this case study. They started with the constraints. They had a tower in an urban environment. So their constraints were the height range, the site setbacks, the tower radius range, and the ground floor area. And then they have parameters, the twisting angle. They wanted to design something that is twisting, the tower orientation based on obviously the sun, and the tower height, the shape of floor plates, the size of the living space, and the size of the core. These are the control parameters. So we have the constraints, we have the control parameters. As you can see, these all are elements that the designer himself inputs to the machine. So the massing then comes where they wanted to specify the massing to be twisting and morphing tower typology. So they chose the typology too. So this is another input or goal value. Afterwards, you have all of these constraints, parameters, and goal values. You input them to an engine, okay? Or not necessarily one engine, obviously to multiple engines, starting with the structure, for example, or the displacement that would use, for example, Canberra plugin in Grasshopper, and then the sustainability energy use that would use Honeybee and Ladybug, and then the spatial quality, and then the sustainability life cycle assessment. So the generative design, here comes the generative design optimization solver, which could be Octopus in here. It could be something, it could be Galapagos. I will talk about this later on, but not in this case since we have more than one objective. So we need a multi-objective optimization solver in order to plug in all of these information and feed the system with all of these parameters, constraints, and objective, and then come up with a solution to reach the final stage of decision making and evaluation and analysis that will be part of the human component. So in the same case study, their optimization goals were mainly three. They wanted sustainability, they wanted structure, maximum deflection, and they wanted spatial quality, the spatial index. So in here, these are two quick demonstrations of how they did the study. We start with looking into the constraints, the requirements, the parameters, and the goal values. Here it's showing you the massing parameters that they input. To twist and to morph, number of towers, and then they do the structural parameters. They give it the core radius, the floor count, the skin, to generate the structural analysis in Carimba. And then comes the goal optimization, or the optimization solver, using Octopus. So Octopus now is generating solutions, thousands and thousands of solutions, and then giving the results in this graph that we will talk about later on. Close to 2,000 iterations generated, and then it refines it. 36 of the most optimized iterations were selected and further analyzed, and then it will further analyze, and then the human component will come to even further minimize and analyze the solutions to reach to the ultimately ideal solution. So Octopus as an optimization engine. Here we zoom in a little bit to the engine that I chose to focus on, because generative design is a very vast, very big topic and very wide open topic to talk about. There are millions of engines and techniques to do generative design with, but I focused on Octopus for this research. And Octopus is a plugin developed by Robert Verlinger at the University of Applied Arts in Vienna. The plugin performs evolutionary processes to parametric models in order to produce several solutions, then runs recursively to produce a number of generations, refining the outcome in each new generation to comply with the goal values. and parameters that are defined by the human in the Grasshopper canvas. So it basically takes your input, takes your parameters and your goal values, and then provide solutions to the problems that you gave Octopus, and then it keeps producing generations, and each new generation would be an improved version of the previous generation. So we have two types of generative optimizations, the qualitative and the quantitative. The qualitative type is it means when the design as a whole is being optimized. So you are trying to generate the design or the form of the building. For example, here in this image on the left, we are generating the form of a bridge and the structure of the bridge. How does it look like? The massing of it. To begin with the design development. So we don't have a fixed design yet. We have the site and we have other fixed parameters and other fixed constraints, but the design is still vague. So this is the qualitative. You will need to give the computer more freedom and more flexibility to be able to generate various diverse designs. Versus the quantitative is more specific. The quantitative optimization happens when you have a fixed design or solution and you need to, for example, optimize the position of columns for a pre-designed steel structure. So the steel structure is designed and ready, but you need to now identify where the cluster of columns will take place. How big are the columns? How many columns do we need? So this is the quantitative, and it will be more specific and it will be more defined since you have more restrictive constraints and parameters. So we have Galapagos that exist in Grasshopper long time ago, even before Octopus. And I want to talk now really quickly about the difference between Galapagos and Octopus and why to choose one or the other. Galapagos is an existing component in Grasshopper, and it's single objective. It optimizes one goal value at a time, and it can work for people who are learning an introductory level. It's less complicated than Octopus. Octopus is a plugin, a very recent plugin, a further development of Galapagos, and it is a multi-objective, so it can carry 2 or more goals and optimizes 2 or more values, and it is more advanced. So if you want to start with the design generation, you can experiment with Galapagos first and then try moving forward to Octopus. Now I'm going to quickly talk about the Pareto front in Octopus plugin. So Robert, who started the Octopus plugin, he used the Pareto front concept to reach the optimal solutions in this space. And this concept stands for a set of solutions that are non-dominated to each other, but are superior to the rest of solutions in search space. And this concept is used in the Pareto graph. You will see later on in my introductory tutorial and in the interface of Octopus. This is the Octopus interface, and right in the middle is where they use the Pareto front to come up with or generate these solutions that you see, generations. In here, I want to talk about the interface of Octopus. Once you double click on Octopus component, you will get this page, or you will get this window. And number 1 in the middle is the middle space, the solution space. This is where you can pan and rotate around your graph. I'm showing this in my quick demo, but it will be nice to also explain it here in the slides. Number 2 is the context menu. If you right click on any of these little cubes or little values or little, let's say, design solutions, you'll get this context menu. And then number 3 is the generation timeline. If you go roll back and roll to the right, it will show you all the generation span and how it changed, how it evolved, how these meshes or how these little cubes evolved and changed on the graph and values. The control buttons, number 4, you start, you stop, and you reset your optimization process. And then number 5 is the algorithmic behavior, where you can change the behavior of the algorithm and play with the algorithm of it. Number 6 is the view settings, how you want to view your graph. Number 7 is the conversion graph. Number 8 is the generation details, how long it took to generate a specific generation and how the time it's taken to generate, for example. Number 9 is the value distribution of parameters as a zigzag graph, so it's basically the parameter graph. And then number 10 is the list of, here at the bottom is the list of goal values. So I want to also quickly elaborate on the solutions and diversity. I'm sure you're wondering how does it randomly generate solutions? How does the computer chooses these solutions and narrow down the solution options and then generate hundreds more, and then narrow down the option and then generate hundreds more? I basically explained it now, but it starts with the mutation that creates different variations, and then the optimization engine starts to eliminate solutions that are far off the goal values or far off the parameters or constraints that the designer input in the graph or in the system, and then it reproduces and it does the mutation again, so it reproduces more solutions from the most sufficient solutions from the previous generation, and then the better solutions survive to the next generation, and then from there it repeats over and over again, taking the best takeoffs to survive. And so the computer nominates solutions to survive to the next generation until it reaches the ideal goal, based on the principles of producing hundreds of random solutions in the early stages of generations, and select the best ones according to the evaluation of the goal values. From there, it changes them slightly, but by different principles like mutations or crossover, and produces 100 more designs. Then again, selects the best 10 to proceed and continue to improve the design again and again. So it reaches a specific pattern, as you can see in the parametric graph. It reaches a specific pattern after evaluating many factors from the Grasshopper setup, goal values, algorithm settings in Octopus, and how much mutation you want and how long the generation period runs, because it is always different for how long you leave your generation period. So it starts with very diverse random solutions, and then over time it gets more goal specific. Last thing I want to talk about here is how to start Octopus really quickly. You go to food4rhino.com and then you download Octopus, and then you copy the GHA and DLL file into Grasshopper components folder. You make sure that you are there is no block on these folders or on these files, and you restart Rhino and Grasshopper, and you should be able to use Octopus in Grasshopper from there. So in this introductory tutorial, I'm going to talk about how to start using Octopus in Grasshopper. And these tessellations here are generations or solutions that were optimized using Grasshopper script in compliance with Octopus. So the first thing I'm going to start with is I'm going to type in Grasshopper, and I have this example script that I can share with everyone in the file. And in here, I'm going to start by having parameters. These parameters are going to be the constraints or the values that will control the generations for Octopus. So starting with this points population, it controls how many points are populated in the mesh, and then the scale also. So if you look at this here, it controls how many points. You start with really few points and then it gets denser, or even change the scale of the tessellation. So these two parameters, and I'm gonna combine those two parameters together with the diversity, the genetic diversity of Octopus that I'm gonna show you in a second. So the first thing to start with is that we need to add gene pools. Gene pools will help in creating even more diversity in the generations. And I start with randomizing these gene pools first. So now we're ready to start with Octopus. So just as a reminder, to get Octopus, you need to, after you download it from Food for Rhino, you'll have to copy the files, make sure they're unblocked, and then copy them to the Grasshopper component folder in your PC. When you go to that file, copy them, restart your Rhino and Grasshopper, and then you should be good to go using Octopus. The first tool that we're going to use here is the Octopus component, and this has the genome or the variables right here. So we connect the G with, and then the objective on the right. So we connect these with the variables that we have. Hold on to Shift to be able to connect it to multiple ones. And then right here, you hold on to Shift 2. And then for the objectives, we're going to connect it with our goal, which is to have higher and more distribution in the X and Y plane. To start up with the Octopus interface, you'll have to double click on the Octopus component, and this interface will pop up to you, and this is the default interface view for Octopus. In here, this is the solution space in the middle, and it's very easy to pan and walk through. Here is where you're going to get your solution. If you have two variables or two objectives, your solution will be made in 2D here on the surface. If you have a third variable, which I'm going to add right now, so we have the two variables right here, and I'm going to add the diversity parameter to make the optimization work in 3D. I'm also going to input a maximum of 10 just to give it more constraints. As I said earlier in the slides, these are the controls right here where you start, stop, or reset. And then in here, this is the timeline, the generation timeline. Here you can see the view settings and then the scale. This is the list of goal values that you have, and then as I said earlier, here is going to be your solution space where you're going to have the generation graphs. So the first thing we're going to do is we're going to start the generation. So now it's evaluating individual solutions and creating multiple generations. It created one generation right now. So when we say generation, it obviously does not mean that it's just one design solution, but it's hundreds and thousands of solutions. And then it picks, it minimizes them, it crossovers, do the mutation, and picks the more ideal solutions that can survive. And the more you leave it to run, the more your graph will be will have a specific pattern. So it starts more random, and then it starts to define itself the more runs it goes. I'm gonna stop right here at 5 generations. I think that's good enough. So now, as you can see, generation solutions stopped, and you can see all these solutions floating around this graph. And if you go here to animation, it gives you a turntable of the graph. You can easily hover over these solutions, and it will show you on the left side of the left bottom side of the screen how it looks, how the curve looks like on the parameter graph. And for example, we can highlight one of the solutions, and then we will choose to reinstate solution, and that will show us the solution in the Rhino 3D. So this is how you look at the generated solutions, the variation of them. You can also mark the solutions. So for example, I mark this one, and it will also mark it in the parameter graph. So you can mark preferred, you can mark preferred gene, and you can create this as a Grasshopper state, so it will transfer all the information from this object to your Grasshopper parameters. Once you want to start generating these as 3D meshes in Grasshopper, in Rhino, you can just go to your script and start baking them. And there you go. So this is a very simple, quick example of how Octopus works in Grasshopper and in Rhino. For sure, this can be utilized for much more complex problems like site analysis, and Octopus is made also to be complied with other Grasshopper plugins like Ladybug, Honeybee. So if you want to do some energy use optimization, or study the structure of the building and optimize solutions for the structure of the building, you're going to need Canberra plugin with Octopus in your script. So this is a very simple, straightforward script for you to start with understanding all the components of Octopus, but then from there, Octopus is very exploratory, and you can explore a lot with Octopus and play with different applications of it to, as we said earlier, from industrial scale to building scale, all the way to city and urban planning scale, with much more high performance, complex problems and really contradicting constraints. In here, I decided to use a very straightforward, simple parameters and constraints just to explain the concept of how Octopus works and how it runs and how it comes into the script and links the variables and objectives to your existing script that you have. I hope this was helpful and straightforward to give you a beginning of how to start with Octopus if you're interested in using Octopus. And now, thank you so much. I hope you enjoyed the video.